implicit differentiation and the second derivative. Okay. So the most focus is it's the second derivative is the biggest focus, and we need to talk about the second derivative and what the second derivative tells us. So first, let's talk about explicit functions. Y equals f of x. Y, and we refer to this typically as the function. Y equals f prime of x is the slope function, and it is a function. Or so, all right. No, or no, I don't want to do that one. So y equals f of y equals f of x. All right, let's just talk about the function y equals f of x. F of a, and this leads into kind of a topic that we're going to get into our next unit, but I'm not fully going there yet, but it is kind of needed. F of a is the output of a at x, the output of f of x at x equals a. That's what f of a tells us. F prime of b tells us the slope, the rate of change of f at x equals a. And we all have a good idea of slope. Why am I keep doing so many terrible mistakes here? F prime of a, I'm sorry. I'm trying to really teach this differently, so it's a little bit more connection of the way we've gone about our topics. And f double prime of a is the concavity of f at x equals a. And so it's this concept and vocabulary word of concavity, which is going to be the probably the toughest part. And it's really technically just an algebra topic concept of it in terms of the concept itself, concavity. So there are two types of concavities. We have, now, some people will call it convex as well. We're not going to utilize that in the calculus. We like to refer to them as concave up. And I like to say like a cup. And with something that's concave up, this is concave up everywhere. And concave down like a frown right there. Now, it should be noted in that when we talk about here, you can be going decreasing in concave up. You can be decreasing in concave down. You can be increasing in concave up. You can be increasing in concave down. So one is not just necessarily telling you the other. So they're independent of each other, and it depends on the function in terms of f prime and f double prime, concave up, concave down. Now we'll spend a whole unit really focusing in on this, but concavity, you should think of concavity as going up or going down in terms of its rate. It's the rate of change. So the rate of change is going down, or the rate of change is increasing, or the rate of change is decreasing. There's a lot of applications in regards to concavity and why they can be very important. And one of the major reasons, and the reason that we're going to cover it, is that concavity enables us to determine relative extrema, and if a tangent approximation is too high or too low. over approximation under approximation. Okay, now this is what we're really going to focus on in terms of how to utilize it today. If a function is strictly concave up on an interval, then the tangent line at any point will lie below the function and therefore under approximate. I know it's a lot to entail. I'm going to break it down a little bit and give you time to just write it down and then go into it a little bit more. So let me give you a chance to catch up there. So if we have some function, and let's say the function is concave down or concave up, like this one, strictly. Now, when I say over the interval, it's over what we're looking at. So we're only interested at the concavity at the point. Now, no matter where you draw a tangent line, if I draw the tangent line here, if I draw a tangent line here, if I draw a tangent line here, these tangent lines will all be below the actual function. One of the things that we're going to be working on, what you're going to do today is you're going to, or we will do in the future, is you're going to approximate future values. So if you can see in this function, the very bottom one I've drawn right here, that one right there, so this line right there, that's a horizontal tangent. You can see that horizontal tangent lies below the graph. Now, there's a lot of things we need to unpack there, and we're going to do that mostly in our next unit. But in the essence of today, and the only thing that I'm asking you in your homework tonight is to determine if that horizontal tangent, or if a line, is going to be below the function or above the function. That's all I'm asking you. All right. Students who don't understand this, or students who don't practice, will say it's the value is negative, or positive, so that means it's going to be over. No, they'll say something about the function value. F of 5 is -3, so therefore it's going to be under. That has nothing to do with it. It depends on the concavity. The tangent line relationship to a function relies on the concavity of the function, nothing else. Once again, the tangent line's relationship location to a function relies only on the concavity of that function over its interval and not anything else. Similarly, if a function is strictly concave down on an interval, any tangent is located above, and thus an over approximation. Now, how are you going to find that? Well, the biggest thing is that you're going to be finding, so, and this is regards to your homework, um, to determine, find f double prime of A. If f double prime of A is greater than 0, concave up, tangent is below. If f double prime of A is less than 0, concave down, therefore tangent is above. And I know it feels like it goes against it. Well, if it's concave up, why is the tangent below? Well, just like I showed you visually, that's the reason why. Now, I was a little bit more specific in when I defined it. I said over the interval. That will be more important later on when we're going to approximate, when do what's called a linear approximation for functions. And then you want to determine, under or over approximations based on that part. I didn't want to go that far right now and introduce too many new ideas to you in one day. Sometimes when you plug in A into the second derivative, you'll get like 0. You get no concavity. But if you plug in the other point where you're trying to figure out what it is, that's the point you have to do. Because it's when talking about does the function over under approximate, you have to look over. You can only answer that question if the concavity is strictly concave up or strictly concave down over the interval from where you make your tangent line to where you want to approximate. That's the technical. I can get technical with you in regards to those concepts, and I try to introduce them, but I also want to make sure that we don't go really beyond how the AP is going to push you with that material. So that's the second derivative. We could do that with explicit functions, and we can do it with implicit functions. You already know how to take the second derivative with explicit functions. You just take the derivative of the derivative, and the same is true here. Now, most of the times, you know that in implicit differentiation, most of the times the derivative is a fraction. Because of that, that means that the second derivative almost always requires the quotient rule. So just as a reminder, when we talk about the second derivative, we use a notation d squared y over dx squared, which is really just the derivative of the derivative. So that's why the notation looks like the notation of d squared y over dx squared. That's why we use this notation for the second derivative, because it's the derivative with respect to x of the derivative with respect to x of y. That's what we are doing. And of course, to find d squared y dx squared, to find, and I'll just try to refer to it as by its actual name, to find a second derivative, you first have to find the first derivative. Makes sense. To find a second derivative, you will need to find a second derivative, you need to find the first derivative, and you will most likely need to use the quotient rule. Don't worry about simplifying. There's two types of questions you're going to be doing. So may be asked to find the second derivative at a point, or something based on concavity, or something based on tangent over under approximation, or you may, and it's the last part before I'll break for you to write, copy down, may be asked to find the second derivative in terms of x and y, only x or only y. So therefore you need to replug in dy dx and or original implicit. All right. Any more time to write? I'll take silence as a no. So in this example, I'm going to give you the implicit function x squared plus y squared equals 25. Now, for those of you who have a strong understanding from your pre-calculus days, or Math 3, this is the equation of a circle with a radius of 5. It's an implicit function because we're not solving for x or y explicitly. And the first question is just a review question. We're going to find, find dy dx. All right, so there's nothing special about question A. It should be something that we all feel very comfortable at this point in time. If you don't, there's something wrong. 2x plus 2y dy dx equals 0. 2y dy dx equals negative 2x. Therefore, dy dx equals negative x over y because the 2's cancel each other out. At this point, with how long we've been going over implicit differentiation, this is about as easy as an implicit differentiation problem goes. This is purely review. There should be no questions or any issues finding that. If you are having trouble finding dy dx for x squared plus y squared equals 25, well, first and foremost, you better be a student that's coming to tutoring. You cannot be struggling at all at any way with that question A, if you expect to do well. I gotta do a hard line somewhere in terms of like a checkpoint. But B, now let's get into something new. Okay. So B says that we want to find this, which is the second derivative, in terms of x and y. And this is a very common question where they don't just say to find a second derivative, they say to find the second derivative in terms of x and y. It's the most common one when they do something with the second derivative. All right, so we're going to do basically what we have done in the past. We're going to take the derivative of both sides. So we're going to take the derivative of dy dx, and we're going to set that to the derivative of negative x over y. So you're technically doing implicit differentiation. Now, you don't really need to show that, but it should be understood that that's what's being done. The left side, the derivative of the derivative, is the second derivative, okay? So you can go directly to that purple line right there. And now we use the quotient rule. It's a little bit tougher, but should still be up everybody's wheelhouse to be able to do. What is this derivative of the right-hand side? I need participation now. What is the derivative of negative x over y with respect to x? I'll wait. Is anybody even there?
I don't think so. So if dy dx parenthesis s negative x equal over y, so the total is negative 1 over y?
No. That's very worrisome that you took the derivative of each of them divided by each other.
So I don't know.
Negative y plus.
So Jerry, yeah, you're jumping the steps, but so it's -1 times y
plus
minus
dy dx, which would be 2y, okay, times negative x all over y squared.
Yes. You cannot be taking the derivative of the two, just dividing them by each other.
So we use the equation of fg and gf over es1.
Explicitly said that you will most likely need to use the quotient rule. And it's almost always, if your derivative is a fraction, you need to be using the quotient rule. Failure to do otherwise results in 0 points. There is no good effort when it comes to AP calculus. So that's the derivative, but does this meet the requisite that the question asked? Is this the answer? Yes or no?
Yeah.
No.
No, you didn't simplify.
No, it's not about simplifying.
Well, plus the wait. What's it equal? Negative x over y equals the other equation? I don't know.
You got to use the yes. You got to use that. Yes. So the question says in terms of x and y. So we have dy. Right now, this is in terms of x, y, and dy dx. It is currently. We want it in terms of x and y. So it's as simple as substituting. Now I multiplied the negative signs and stuff like that. So I put a plus x and substituting in dy dx. So the answer is required to be written in terms of x and y. Without writing it in terms of x and y, you'll likely either get only one of the 2 points, or even if you get the idea of the quotient rule, you would get possible that the question can still only be a 1 point question, and therefore you get 0 points because you didn't answer the question in terms of x and y as it is requested to do. Right? This derivative, while it required you to take the quotient rule, should still be relatively straightforward in terms of the work. Now, you at least, if you need to utilize the u and the v and use the u prime v, v prime u aspect of it and put that on the side, hey, that's okay. That's more than okay. It's okay to do the work and take a little bit longer and be a little bit more detailed than it is to get the wrong answer with this type of material. C. And it should be pointed out very explicitly to you, it sounds like, that the answer does not require simplifying. Now, of course, if it's a multiple choice question, you're going to have to do that. You use the algebra manipulation. But I'm going to do that in the next question because the next question basically requires you to be able to use simplifying or simplifying techniques. Hate the word simplifying. It's manipulation. Find the second derivative in terms of y only. Ooh, so now it says I do not want you to write it in terms of x. I want you to only get it in terms of y. Now, we could really clean this problem up and it'll help us, or there's actually a step that we can do in terms of substituting. So the main thing here is, what do I have to do to my previous answer in order to get this? What do I have to do? I have my derivative right now is in terms of x and y. This question wants me to find a derivative in terms of y only. So what am I going to have to do?
Get rid of the x's.
Get rid of the x's. Okay, how am I going to do that? And this is where it's tough to, and I got to be a little bit more technical again. We're not getting rid of the x's. We need to substitute for the x's. We need to find a relationship for x, or a relationship of x in the way it's written. So simplifying or cleaning it up might be something that's very helpful here. So first off, the second derivative is negative y minus x squared over y squared. Okay, so I clean this up. Negative x over y times x is negative x squared. So right now I have this right here. Now technically right here I can actually break and go and figure it out right here. You have to go all the way back to the original function because you need to find x in terms of y. You need to substitute out x for y, which means you need the relationship between only x and y, which is the original, which was x squared plus y squared equals 25. So what can I do here? What can I do? Now, I could go about solving it and simplifying it, yes. But what can I do right here? What is a possible way, and it would give me the final answer if it was an open response, and I would just do it here. I need to substitute out what? I need to substitute for what?
X squared.
X squared. It's as simple as that. What is x squared? And so I need to substitute for x squared. And what is x squared?
X squared equals 25 minus y squared.
Perfect. Boop. And that would technically give me my answer. However, it's going to be harder to simplify. So if this was a free response question, then you should just plug it in and be done with the problem. In other words, the second derivative is equal to negative y minus parentheses 25 minus y squared, close parentheses, over y, all over y squared. Call it a day. All right. Now you can do that first step anyways, regardless, if you want to, or you can clean it up before you plug it in. And it also turns out to be when you do that, you can plug in a little bit easier. So what I'm referring to here is that we could have just cleaned this up first, and you get to the same answer either way. And this is more for the multiple choice questions. If it's free response, and as of right now, I don't know if there's going to be multiple choice questions. So once I find that answer, I can, if I find out there's no multiple choice, and I can attack the teaching a little bit differently. But right now, I have to include both. We multiply by y on both sides. If I multiply top and bottom by y, I get negative y squared minus x squared all over y to the third. And then I do my substitution, which gives me negative y squared minus parentheses 25 minus y squared all over y cubed. The y squareds cancel each other out, giving me that the second derivative is equal to negative 25. Hey, get over here. Over y to the third. This is how it would look in multiple choice question. This is 100% correct for free response question. In a free response question, you never want to worry about anything about simplifying. You don't want to do it unless it's going to be something where you have to take like a next step on the problem. Then it would be to your benefit to do some simplifying or algebra manipulation in order to be able to attack the next step of the problem. But if there's not, then you answer the question in terms of the most direct way that you can possibly do. Now, I do want to point out that you can use other letters. It don't look like I have enough time, so I'm just going to do a question D right here. Find the equation, or actually I'll do it just like the homework does it. I'll do it just like the homework. Show that there is a horizontal tangent at 0, 5. Determine if above or below function. So we want the tangent at 0, 5, and if we want to show that there's a horizontal tangent, all right? We want to show that there's a horizontal tangent. So how do I show that there's a horizontal tangent? How do I confirm? How do I show? How would I find a horizontal tangent? Well, I'm not trying to find here. I already told you it's at 0, 5. And if you answer there's not a horizontal tangent at 0, 5, you know you're 100% wrong, because the question is not asking if. It's telling you that it is in the show as your first step and your first point of 2 points. So what do I do here? Quick, we only got a minute left. We're going to be done already.
Plug in.
Plug in. Plug in what?
The 5 and the 0 for x and y.
Plug in where?
Into the equation.
Into what equation?
Hey, baby.
There's no baby. There is no baby.
And you're really not.
No.
And the derivative, negative x.
There we go. There we go.
So
I heard both of you saying it right there. Into the derivative. Into the derivative. You plug the point into the derivative. Horizontal tangents are based on the derivative. So dy dx was negative x over y. So dy dx equals negative 0 over 5, which is 0. So boom, we just confirmed there's a horizontal tangent. Now, I need to confirm and see if it's above or below. So I plug in. So that confirms it. I'm going to plug into the second derivative, which was negative 25 over 5 squared, cubed, sorry, which I don't actually need to find a number. I just know that this is less than 0. So that tells me it's concave down, which means that the tangent line is above. This right here is the work and then the answer. All problems basically require work and answer. All right. So what you need both of these to get the second point. You need to show the work. You need to show that the second derivative was negative and then say above. If you just try to guess it and go above, haha, I guessed it and I got it right, haha, no, you got no points on the exam. You would have to show that the second derivative is negative to know that you're talking about the second derivative. So once you guys started talking, it got it down a little bit faster. I wish I could have done a little bit more in terms of just another example, but that covers everything that we wanted and I wanted to get through. It is 9:51. I will see you tomorrow.